Hello, my friends of Hatari Labs. Please have a very nice day. Today we're going to do a simulation of the radial drains for mine tailings drainage with MODFLOW. Okay, so this tutorial is related to when we deal with tailings drainage, we are dealing with a drainage of a very low K, of a material of very low hydraulic conductivity. Therefore, the use of pumping wheels is not feasible because actually we are not going to have water coming into our wells because the conductivity of the porous media is very low. So it's more convenient to use radial drains. In order to do that, we are going to have to make a model in order to assess the feasibility of those radial drains. So we will use model muse. Okay, here we are going to insert a new MODFLOW model that here is more declarative, but you have to insert a EPSG that, let's say that for Peru is 3271. Next. Okay, and now we are going to set that our model will be, okay, so 48 columns, 24 rows, 10 meters, 10 meters, one layer because after that we are going to divide it by 3, 5,000, 5,012. Okay. The top is 12. So our aquifer, our tailing materials is just 12 meters thick. So don't worry. Finish. And now we have our model. Okay. Cool, great. Now we are going to use MODFLOW 2005 plus packaging programs. Since we are dealing with low case, we have to increase our iterations. We go with LPF, and on boundary conditions, we will use the drains will be model conceptualized as general head boundary condition. Okay. It could be also drain, but let's say that we have general head boundary conditions. On solvers, on the PCE solver, we will use 500 iterations with 50 inner iterations. Okay. Okay. On the sum budget, we will activate the sum budget. Okay, great. Let's say that it's okay. Okay. Then we go to layer groups, model layer groups, and then we define this as convertible. On the discretization, instead of having one layer, we will use 12 layers. Okay, great. Again, we go with MODFLOW time, model MODFLOW time, and then we are going to simulate 1,000 days. So 1 day. My preference is to use the international standard, so meters and seconds. So 1 day is 6,400. This is 1 day, but 1,000 days is with 3 more zeros. Okay, great. This here it will be calculated in 1,000 days. Will not calculated the 1,000 days, but every 100 days. So in 10 time steps. Okay. and it will be transient. Transient. Okay, great. And model options. Okay, we go to model options, and it could be possible that I mean, since as well we are dealing with low K, that we don't reach the convergence criteria. If we don't reach the convergence criteria, it's better to, I mean, we won't reach the convergence criteria, but our model won't have a, that, but we will, our water balance of what goes in, what's going out of the model will be really close to zero. So that's, I mean, we are not reaching the convergence criteria, but in the end, is the model error is not so huge. I mean, if you play around, if you go further with this exercise, you can get the model working without this option that continue running even the source close criteria is not met. But this is up to you. I mean, the tutorial won't reach to this part. Okay, now we go to the model parameters. So grid, the data sets, the data sets, required hydrology. So kx is 110 to the minus 1, 10 to the minus 8 because it's tailings. Tailings is, this is almost a base tailings, mine tailings. Okay. So, and then on the anisotropy, since it's only 12 meters thick, we are not going to deal with, not going to deal with higher anisotropies due to gravity because it's, we are not dealing with 100 meters aquifer thickness, but with only just 10 meters. Okay. So we say Kx and Kz is equal to Kx. The initial head is just half a meter below surface. Pool, the specific storage is 110 to the minus 6. Okay, pool, that's great. And this is 0.02. 110 to the minus 8, 0.02. Yeah, okay. Great, that's great. Okay, apply and close. Cool. Now we are going to define our caissons. So what is the meaning of the radial drains? The radial drains are structures that, I mean, radial drains. Let me show you what we will represent in our model. Caissons. Okay, cool. This is a good representation of what we want to do. So here we have our collector well, and these are the lateral drains that are radial drains that are the ones that will be where the water will be dripping into the drains that will be collected on the collector well. Okay, cool. Yeah. So we are going to insert two of them. The first one that we are going to insert is located on, let's say it will be, let's say that it will be here. Let's count 14, 14, 15, this one. So this one will be just to select where the caisson will be located. Okay, here. And I just change of color. This is the collector well. Okay, Cool. Maybe I will put another. Yeah, this is the collector well, and then I need another connector well that will be 5, 10, 14, 15 here. Here I just need another collector well, and this is another collector well. Cool. And those both are the collector wells, but actually those collector wells are not the ones that collect seepage. What the drainage, the seepage drains are the ones that collect the infiltration. So we are going to insert one of them, and then we are going to do a polyline sections. So first of all, I do one here, one that goes, and every drain has 60 meters length. So let's see, is they intersect 6 cells. Yeah, cool. This is a drain. And then I change off. Let's see that this is the color, and let's say, and since we want, I mean, the aquifer is 12 thickness, is 12 meters, has a thickness of 12 meters. So we will try to put the drain as lower as possible. So it will be at 0.5 meters, because actually 0 is the bottom of the model. Okay, let's say that's cool, and then we go here, we go from here, we go from the beginning to the end. The conductance is direct. What else? The boundary height is 0.5, and the conductance is 0.001. Okay, okay, and this is my first drain. Okay, I have two options. Whether I create by like one object per drain, so in the end I will end up with 16 objects, or I do composite objects, or like what is called a polyline sections. I would prefer to use a polyline sections because it's less work, because all the drains will be defined by with the same object, so I can apply different conductance, different parameters, but to the whole set of drains. Okay, so it's my option. So I just said here, and then I put one that goes from here to here. Then I need to do that in order to do successive. Okay, and then I deselect and then select. And then I go from here. And then I made a mistake here. This has to be longer. Okay, okay, these are the ones that are whether on the X direction or the Y direction. But now I can do the inclined ones. Oops. Here I made a mistake. Here I just put it here, and this one I press delete, and then I delete this vertex. Then I press this one again, and then here to here. Why not? And from here Oops, sorry again. Doesn't matter. I mean, if you do it by your own, you uh, you will find a way to do it. It's just persistence. Like I say, nobody was born learning with MODFLOW knowledge, so everybody here has to learn somehow. So here, 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 here to here. Um, from here to here, and from here to here, and from here to here. Okay, and then I go from here to okay, here. Okay, so I have, these are my drains now. And this is just one object. This is very practical because when I select it, I select the whole. Do you know? Do you see? Yep. And this is, I mean, and if I want to change a parameter, I will change it to the whole set of 16 objects. Okay. And this is very practical. Okay. So please save. So we say save. And we are going to, I will create a carpet folder here that will say radial drains, You will have this, model, these files for you to review on the description, on the link, on the description of the video. Okay, model, radial drains. Okay, cool. And now I can run, okay. Before that, if we play around with our drains like this, our drains has a thickness of 10 meters, and this is not true because actually our drains will be limited to maybe 1 meter or 30 centimeters depending on the drilling technique. So we need to do a refinement here. The topic about refinement is that you can get numerical instabilities if you do higher refinements and you have to play around with the parameters in order to get the convergence. But in order to define or like to play around with a refinement, what I'm going to do is I will do a refinement that will divide these 10 meters cells into 3. So we will have like a better discretization that you can play around with higher discretization by your own. So what I do is I go to with this one, I go from this to this, and then I select and I say I want it divided by 3 and this one divided by 3. Cool. And then I go to here from here, but I want just here that the columns are divided by 3, not the rows. Okay. So cool. Now I have a refinement, so I will have, in the end, I will have a better representation of the drainage impact. But you can play with your own. I mean, you can play with like refinements to the 0.5 meters or maybe 20 centimeters. It's up to you. And then I will go to here, and then here are my drains. I have used this option. Okay, cool. So save it again and then run my model. Cool. It's running. And then I have a non-convergence at the beginning. Well, it's because of this non-convergence is related to the conductance and so on. Please read the list file. Okay, so now we are on time step 9 and then finish. Okay, the 10,000 days. Okay, then we go to the water balance and they say that what the storage, I mean that is the decrease on the water table is the one that is giving water to the water that goes into the head into the horizontal drains. Okay, so what I am going to do is I'm going to import results here, drains AFD, and then I'm going to import it as control grid. And then here I'm going to import a cross section, data sets, optional model results, water table P1, S1, S10, and then here this is and on the contour data I will use as well light blue to dark blue, and then here I take out the active edge. And as you have seen here, the radial drains are capable of draining this low K material. And this is great because otherwise, and I have made another example before, with horizontal wells, that wouldn't be possible. Okay, so because of the low K of the tailings. Okay, just to finish this tutorial, I will look for the water balance to see how much water is draining those wells. So I use the groundwater, and the GW chart, and then I go to water budgets, file, open, Radial drains, and then here I have this. Okay, and take water. Okay, cool. Now I don't have anything because here on data, edit data sets, I need to, and required some budget zones, I need to put this value to another index, because actually this is an index, this is not a value. Otherwise I won't have. Okay, I don't need to run the MODFLOW model again. I just need to run the sum budget again, only the sum budget. Okay, okay. This is the simulation of some budget. So now if I do the groundwater chart, I go here and then I say water budgets, file, open, Radial drains, and then it says it asks for a discretization file that is the same here. Okay, I take this one out, and that says how much water is draining through the horizontal drains. This is in cubic meters per second. Maybe I can say I can put the cumulative. Okay, so at the beginning we have the drainage is on the first 100 days, it will have drained 600 liters, cubic meters per second. No, cubic meters on the first 100 days. And on the 1,000 days, it will have drained 1,800 meters, like 3 times more. Okay, so it's almost logarithmical. Okay, so this is the drainage that will be collected by the radial drains. Okay, so my name is Saul Montoya. I work in a very interesting project that is called Hatari Labs. Hatari Labs is a Hatari Labs is a website dedicated to knowledge sharing on open source software in water resources. So what we like is to give tutorials and articles on what can be done with open source software in order to assess different cases. Okay, so we are going to publish a lot of tutorials. Please follow this video on YouTube, on this YouTube channel, and please share our post on the social networks that you have, and we have some webinars that you can join. All the webinars are free, and here we have some posts. We have a blog with many posts as well, and we have a Facebook, Hatari Labs, as well, and you can follow us there. And there is a newsletter as well. Like here, if you go to the blog, you can subscribe to the newsletter. You can drop your email here, and we will have we have a nice time sharing knowledge, and we want to do it more. So if you have an idea how we can do a tutorial, or to do a tutorial on something, please send us a contact form, and then we will review it. Okay, so please have everybody a nice day, and I hope that you have an excellent day with your staff, and then that you have enjoyed this tutorial, and we hope that we can see you in another tutorial. See you, bye bye.